In previous video, we have seen that how we'll use TF, IDF, and what is its important. Now the main questions that's now come into our mind. Then IDF, why we use lock in IDF? Why we not simply use this just direct inverse formula? Why we will use lock? So let's, if you remember, the formula of the IDF is look like this. IDF is of a particular word, let's WI, and the data corpus is DC. Its formula is log of capital N by small ni. Okay, and this is the formula. If you remember here, the capital N is what? Capital N is the number of documents in the whole data corpus, number of documents. Okay, and small ni is the number of documents which contains the word wi. It is the number of documents which contains the word wi. Already we have seen this formula, okay, how to build it and what is its important. So actually this IDF give the importance of those words which are rare, means which are less occurred in our whole document. That is the meaning about this. Okay, we have seen these things. Now the questions that have occurred, actually why this log has come into this picture, why these things are happen. Okay, let's see. So before understanding this thing, actually I am not going to explanation through mathematical point of view. I'm giving the geometrical intuitions of it. We will try to understand why actually this we will use this log formula in IDF. We'll try to understand this thing in geometrical point of view. Geometrical point of view. Okay, so to understand it, one thing that we have to understand, the Gibbs law. What is this Gibbs law? What is it? It's a well known and most popular and basic fundamental theorem in the NLP areas. So let's try to. So if you just plot the histogram of the words that occurs in the English language, if you plot the histogram of word occurrences in English literature, okay, if we plot this histogram, then the plot actually will look like this type of plot we will got. It's this type of plot. Okay, so its plot will be look like this type. So in x-axis there have the words, means wi, and in y-axis we use the frequency of each word. Okay, in frequency for we will use. So the plot is the Gibbs law, which will look like this type. This type of plot we'll got. Okay, that means the most least amount of words are more frequent, and there have the very few words that are the less frequent in our whole data sets. So you can consider these things. If you plot this like a Wikipedia documents over, whole Wikipedia documents over, this kind of histogram plot we will see. Okay. So here you can think this thing like that way. Here the word will be like the, it's a most common frequent word, like e, like each, like an, like that. Like these kind of words are lie on these most frequent regions. If you see, already we have completed the probability and statistics chapter. If you remember, this type of plot we will got in power law distributions. This is the power law distributions. If you forgot it, please, I recommend you, please go to the probability and statistics chapter and just see this sections, power law distribution. See this video, power law distributions. Then you will find this kind of pictures we will got there. Okay. So this, the distributions of that, the frequency of the words, it is the power law type of distribution. Okay, power law, or you can think it is a log normal distributions or log normal. Okay, log normal distributions. And we have seen if some distributions follows, we have already seen in this chapter probability and statistics, if some distributions f, if it is follows a power law distribution, or if it is follow a log normal distribution, then simple, but to transfer this thing in Gaussians, we will use transfer this power law distributions into a Gaussian distribution. We will simple apply here the Box-Cox transformation. Well, simple. If you forget it, please go there and just recap this video. Okay, Box-Cox transformations we will apply it on that, on this distribution. The Box-Cox transformations is nothing, just simple log, it's one kind of log functions apply on that random variable that follows the power law distributions, and after applying it, simple follows the Gaussian distribution. Okay, we have seen already this step. So this is the power law. If we apply onto it the Box-Cox transformations, if we apply the Box-Cox transformations of this frequency, means of this distribution, if we apply, so this kind of plot we will got now. Here it will be log of frequency. So this plot will be look like this type of plot we will got. It's type of straight line. Okay, this type of. If you forgot it, just recap this video, then you can try to, you got the answer. Now let's try to understand why actually now in IDF we will use log, because of only these reasons. So the most of the work follows this frequency, means power law distributions. To simple understand this thing, frequency like a linear way. So just see this, how much deviations they are have. Once the most less amount of words are more frequent, and maximum word are less frequent. Okay, means it's kind of 80-20 principle type of things they have follows. Okay, Pareto distributions like of. So in these situations, to visualize this deviations in a linear way. These things are important. Now let's see it through an example. I think it will be better for us. Okay, let's see it through an example. Suppose let in that it side compare through the side by side. Suppose let in our left side we will use n by ni sample, and right side we will use capital N by small ni. Let we will use these two things to compare side by side how much these things is. Suppose let here n is equals to number of data set, number of documents in our whole corpus. Let capital N is equals to 1000. Okay, let it is. And small n, now it's depend on our word to word. If our small n I is like of this the a and like of this word, then this value capital N by small n I is approximate equals to 1. So suppose let I am taking this word the. It's the most common word and most frequent word in the English literature. And if we take this the, so this value will be now what? This value will be approximate equals to 1. Means the is occurs most in most of all the documents. So in that situation, this value n by n will be equals to 1. So what will be this now value? Log a. This value will be approximate equals to log of 1 means 0. Okay. Similarly, each if you consider, it's approximate equals to 1. A is approximate equals to 1, its value. Similarly, its value are for approximate equals to 0. These values are. Now let we have take some value, it's a less frequent. Suppose let I have taken the civilizations. Civilization, let's for an example. It's a most rare word in our whole data corpus. In such situations, what will be the value? It's the most rare word. Let it will better if a in the data corpus DC. It's a rare word. So in such situations, what will be this value? Its value will be approximately equals to how much documents we have. In 1000 documents total we have, and suppose let's in single documents we got this civilizations word. In such situations, 1. Okay, this value will be 1000. So if you calculated this value now, this value will be now this value log of capital N by n, log of approximately 1000. It's near about, it's approximate, it's near about 6.9. Calculate it. So now the questions that come into our pictures, just recall the TF. TF. TF means what? What is the formula of TF? So what is the formula of TF? So if you remember, TF is TF for a particular word. Let's WI, and for a particular document RJ. It's a particular document and it's a particular word of this document. So this formula is number of times WI occurs in the review RJ, and the total number of words in RJ. That is the formula of the TF. Means number of times a particular word WI occurs a single document, and how much There are a total number of words in that document. That is the meaning of the TF. And we will see in a document, in this value, if you like, this value is lie on 0 to 1. We have already seen this thing. This value is 0 to 1. Okay, but the main problem is here. Just see it. If we have not used this lock term on the IDF, then this, for the frequent word, this value is more larger. Just see it. The each, and for IDF, if we not use this lock term here, this value is 1000. Its maximum value 1000, means the number of documents size in our data sets is so large. Okay, and the number of words in a particular document is so small. Because of these reasons, the IDF is dominates the TF, term frequency, because of these reasons. Okay, since term frequency lies on these regions, because of these regions, the multiplications of TF into IDF. So here IDF, the value of the IDF will be lie on like this 1, 2, up to like the number of times the n, capital N. So is a large number. It's a large number. If we not use logarithm. So in these cases, if it is a large number, because of these reasons, these numbers are dominates the TF value. Dominates the TF value. Okay. Now the solutions that the scientist has discovered, instead of using by simple n by capital N by small n, if we used here the log of this, if we use the log of capital N by small ni, if we use this thing, then what this value will be? So this value will be 1, sorry, from it start from 0, like that, means maximum for large value, its value will be maximum 20, like, means that's kind of maximum. If you consider log of 10,000, log of what is 10,000? 10 to the power cube. Yeah, 1000 means 10 cube. Means I'm talking about log to the base e. Here it is will be the log to the base with natural logarithm. So this value will be approximate equals to the, means approximate equals to 6, like approximate equals to 6 point something, it's 6.9 something, like that, like this, means maximum 2000s. So if you only for 10,000 documents, only for 1,000 document we got 6.9. If you have very large number of documents, so this value will be maximum value here, maximum value of n in such situations. Okay, this value will be, so it is less dominant for these situations. It is less, this value is this less dominant of less dominant to TF. Okay, 2 is not a good word. TF, let's dominate TF. Okay, because of simple this reason, because of simple this thing, because of these simple dominations. Okay, if we have not used this log, simple, the large value of the IDF which dominates the small value of the TF. To somehow to handle this, somehow to squeeze this IDF value, somehow to maintain this, means normalize this IDF value, we will use here the log formula. I think you got the idea what is the geometrical intuitions actually behind this, the log, why actually we have taken this log concept. By simply using the avoid the dominations of the TF of IDF, by simply using the dominations. Okay, since TF value is like on 0 to 1, if we have not log on IDF, then TF Trump frequency is easily be dominated by the inverse document frequency IDF. I think you got the idea why this log is important on our IDF.